Okay, we have a pre-recorded talk now. Okay, this will be. Oh, okay, no. Okay. Okay, this will be given by Jakob Pagter, Builder Bolt Stories.
I'm Jakob from Block Demon. I'm here together with Michael and Sasha. We're going to present something we call Builder Vault Stories, which is about some of our learnings building an enterprise level key management system leveraging MPC. The first thing I want to do is I want to apologize for us not being able to make it in person. Different logistical problems came up, but I hope that you will still appreciate our presentation here, and thanks very much for letting us do this. So Builder Vault is a product from Block Demon. There's a link in the bottom of this slide. It was first introduced by Sepia, which was acquired by Block Demon in 22, and the present version is the third or fourth iteration of this product. And as you will see a bit later, it now is highly dependent on something we call libMPC, which is the piece of our software which implements all of our MPC protocols, which are then embedded into the product. We started having customers on this in 19, and today we have some clients, more like the crypto native space with our code running on millions of mobile devices, but we also have more TradFi wallet providers using them in highly secure environments. And so I'm going to introduce here, Michael will take over, and then Sasha will wrap everything up. Yes. So what we do with Builder Vault is something we at least call threshold cryptography. I know NIST use that terminology as well. And that basically means that you're doing key management using multi-party computation. And I think most of the audience here will know that the way this works is that the secret key for symmetric or asymmetric cipher is split or shared into a number of parts called secret shares, and these are held in our system by a number of nodes, and the threshold is number t, and in a case so that you need t plus 1 shares to operate the system, and less won't let you allow you to do anything. Some blockchains support similar security models with stuff like multisig. From a security perspective, you can argue that it's very much the same. From a practical perspective, there are many big differences in terms of privacy, accountability, and so on and so forth. But it all boils down to whether this threshold feature is implemented on-chain or off-chain. And you can see on the right the different primitives that we presently support. We're not going to go into this, but reach out if you have questions. And the way the system is designed is that the shares which are used by our libMPC is held by, in this case, 3 different MPC nodes. And this is really the secure part of the system. Outside of that, we have one or more application which use an SDK that we provide to communicate with these MPC nodes to execute cryptographic operations. Our MPC nodes is available on a number of different platforms, particularly Go, Wasm, iOS, and Android. So this means that you can have, for instance, if you're building a wallet, you can have one node running on a mobile device and another node running in a Kubernetes cluster on your infrastructure. On top of this, we have the SDKs, which are available in a number of different languages and platforms, as you can see here.
Yeah, thanks, Jakob. So what better way is there to see what you can do with the SDK than look at some code examples? So here's an example from the Go SDK, how you actually use this product. So there's some assumptions. First, you configure the nodes. They configure with an API key, so you can access it through the SDK. It also configured with public keys and addresses of the other nodes so they can talk to each other. And then you basically agree on a session ID to run an MPC session. In this case, it's key generation. So first you make a configuration, you provide the URL of a node, you say how you want to authenticate towards that node. It's an API key, it could be a MTLS connection or some OIDC, and then you create a client. Then you take the session ID that all participants in the protocol must agree on, and then you create a session configuration. The session configuration contains the session ID, it contains the indexes of the players that are participating in the protocol. In this case it's 1, 2, and 3. And then you have a couple of nil values. That's where you can specify public keys and addresses of players. If you don't specify anything, it uses the players you have from the configuration file. But you can also leave the configuration file empty and specify players dynamically here. And then comes the actual protocol. You take your client, you access the ECDSA functionality, and you will say you want to generate a key. You provide a context, as you always do in Go. You give the session configuration. You have the number 2. That's actually the security threshold T, as you saw on the previous slides. You specify what elliptic curve you want to do ECDSA over, and you have an empty parameter, which can be a key identifier. If you have a specific one you need, if you leave it empty, it will generate one automatically for you. The result is you get a key ID back that you use later to refer to this key. So what good is a key if you can't use it for signing? So you can do the same thing. If you want to sign with that key, we still have the client, we agree on a session ID. You do a session config just as before. You hash a message you want to sign, hello world in this case, and then you call the sign functionality on the ECDSA client. You give the session config, tell it what key you want to sign with. If you want to use BIP32 to derive a key from this master key, you can specify the derivation path here. Here it's just empty, and then you give the message hash. So same thing as before. The difference is here that you get a partial signature back, so you only get a share of the signature. So once you have gathered these from all the nodes, then you call a method in the SDK that finalizes the signature from all these partial signatures, and then you get the actual ECDSA signature out. So from this point on, it's actually fairly straightforward to see what's going on, but let's dive a bit deeper into the system to see what is actually happening when you call this from the SDK. So there are 3 central components we use for running our protocols. First, we have something we call the executors. They know how to get data to and from other nodes for a given session. Which one you get depends on how the node is configured. You can get one that knows how to talk direct TCP connection. It can talk through Redis, message broker, RabbitMQ, all other AMQP. It can use WebSockets, but there are different executors for doing this. And the executor will actually create a runner that's used to orchestrate a single run of the protocol. So it basically maps the session ID to a runner. And the runner uses methods from the executor to actually transfer data between the participants. It doesn't know how to communicate. The runner is from this component Jakob referred to as libMPC. It does a lot of other stuff. It performs authenticated key exchange using a Diffie-Hellman key exchange, then it crypts, authenticates data, negotiate protocol versions, because you can have different versions of the ECDSA protocol. It turned out that just because we introduce a new protocol, you can't break all previous instances because customers don't like that. It also makes sure that all players participating in the session agree on the metadata, like message to sign, who's participating in this session, their public keys, etc. It provides a common nonce to all players, and it runs a coin tossing protocol, so it has some joint random value you can get afterwards. That's, for example, used to derive the key ID. And most importantly, it creates a number of channels between players. So you can actually, when you do the protocol, have a way of sending data to the players that's independent on how the executor works. Finally, the actual MPC protocol, here DKLS23 for ECDSA, will take the runner and use it to run the protocol. And in doing that, it will also call out to other sub-protocols to do some work that's, for example, EC key generation is used by many protocols. We don't need to implement that separately for each protocol. We can just use a building block we already have. So let's see what's actually happening underneath. What happens when a node receives a request from the SDK, for example, key generation? Well, at first, all the boring stuff happens: authentication, authorization, logging, passing input. That's what you always have to do, whether or not it's MPC or some other system. So once all that's clear, you're allowed to generate a key. The node is going to ask the executor for a runner. And that's basically a single line. It takes the session config provided by the SDK and creates the runner. How it creates that, in this case, it's a packet runner. So you tell it what player am I, what are the other players, what are the keys we want to use for the key exchange part. Since it's a packet runner, it communicates by sending blobs of data back and forth between the players. So it has a send function that takes the index of the player that's supposed to receive this data and the actual data. So if you give that to the runner, it will just call that whenever it wants to send data to another player, and then the executor will have to fill out this function with how to actually send the data. Once data comes back to the executor, it can inject it into the runner by calling the receive packet method with the number of the player that sent the data and the actual data itself. So now that the node got a runner, what can it do with it? Well, it's going to give it to the MPC protocol. In this case, it's ECDSA keygen, which is called with a context, and the number, again, the threshold, the name of the elliptic curve, and the last parameter is the runner itself, and then it has this weird store key material function, and that's basically a function that's called by the protocol when it wants to persist key material to disk. Why is that part of the keygen protocol and not something returned by keygen so you could store it yourself? And that's basically because we want to ensure that when the protocol actually completes without an error, the key material is stored in the database. If we store it afterwards, we can get in the unfortunate situation that some nodes think the protocol succeeded, I have stored my key material, everything is fine, but one node actually failed to do that, and the other nodes don't know, so they take the public key, they derive an address, they transfer lots of funds to it on the blockchain, but the private key doesn't exist because one of the nodes failed. So by doing it this way, they have an additional acknowledgement round after they have stored the key material, so you know it's actually persisted. So once you have the runner, you give it to the actual protocol, and here is an example of how that protocol could look. The runner has a run method that takes a context. It takes all the protocol versions we support. It's a list of protocol versions. It takes some session parameters, and it takes a callback function that is given a session. And the session is basically all the stuff the runner figured out for you, like what protocol versions are you going to use. Here are the channels you can communicate over when you want to talk to other players, and so on. The session parameter is a callback function because the function gets the negotiated protocol version as input, because you might want to have different session parameters for different protocol versions. And here you can say the runner will generate a nonce, how long should it be, how many channels do I want to have between each player. If you have a protocol that can do 3 things in parallel, maybe you want 3 channels, here we want 2, and then you have all the metadata you want participants to agree on. And when you come to the actual protocol, you can see you can just ask the session, get all channel zeros, then you get, because you ask for 2 channels, you have channels 1, 0 and 1. And for each, it's a set of channels because you get all the channel zeros for all players. So for example, if you take index 2 of channel zeros, you get the first channel to player 2, and you can also get the second channel to player 2. These channels are just in Go, it's a read-writer. So you can write data to it, you can read data from it, and then you actually implement your protocol on top of this, and the runner and the executor will handle all the communication, authentication, and stuff you need to do the protocol. So that's the simple way of doing it. For one instance, the executor can track a lot of sessions, but at some point you want to have higher throughput than a single node can support. We have customers wanting to scale to thousands of signatures per second, and or they want redundancy, so they always ask for load balancing. Can we just replicate one node and do round robin when all requests come in? The answer is, unfortunately, no, because sessions are stored in memory on a node, and we basically need all connections to go to the same node. And here's an illustration of the problem. You have node 1 is behind a load balancer, so it has actually 2 nodes to distribute the load. There's an SDK that wants to start an operation, so it calls the load balancer instead. It gets a random node, and then the session is also started on node number 2, and it's also started on node number 3. So when it starts on node number 2, at some point it needs to send data to node number 1, so it calls the load balancer. It gets node 1A. That's fine. Node 3 will do the same thing, and the load balancer will just give it node 1B. This session is never going to complete because node 1A is missing connection from node 3, and node 1B is missing connections from the SDK, and node 2, it doesn't even know the session started because the SDK call didn't get to it. This is a common problem with load balancing. The solution is usually sticky sessions. So you have some identifier that ties all sessions to a specific node. Unfortunately, we have different communication methods here. The SDK one, that's HTTPS. The other might use an MTLS connection, and there's really not something a standard load balancer can do sticky sessions in this case. So the easiest way to solve it is don't use direct connections between nodes, use a message broker like Redis. If you name the queue or the list in Redis after the player in the session, players can just start sending messages to other players without knowing exactly where they are. You just send it to the message broker. Of course, now you can scale well, but the bottleneck is the broker itself. But sometimes you need a TCP load balancer. Some customers say, we can't do a message broker in this case. We need to use a load balancer. For example, the application load balancer in AWS. So we solve this by sending a routing ID as the first bytes in a session, and also including it as a header in the SDK call. The routing ID is just a hash of the session ID. And we use that for doing sticky sessions. And we send it before the TLS handshake, because if it's encrypted, it's difficult to do routing based on it. And then we let each node act as a load balancer. The advantage of this is that it actually works. The disadvantage is that each node must now handle twice the number of connections, because it receives a connection, it looks in the database, who is going to handle this. If there's no one handling it, it can take it himself. If there are other nodes handling this, it needs to forward the connection to the other node. Now it's just relaying data back and forth. We have some stuff where we want to reuse TCP connection instead of establishing a new one all the time. You have to disable that when doing this load balancing, otherwise you don't have any load balancing, because the same node is just proxying multiple sessions to the same node. To communicate with the mobile phones, we introduced something we call the connect up approach, that nodes with a lower index will connect to nodes with a higher index and not the other way around, because a mobile phone usually can't accept incoming connections, so the mobile phone is node number 0, and it only connects out. That's fine for this, but for load balancing, it means that the load is really asymmetric, and the last node in the chain is going to receive a lot more connections. It usually means that you have a fully saturated setup on node 2, something that's quite idle on node 1, and something that's only 1/3 loaded for node 0, so that doesn't really scale well. A better approach is to replicate the entire Builder-Vault instance. So basically have copies of Builder-Vault with all nodes pointing to the same database. And then in the SDK, you just pick which one you're going to do. So you're basically load balancing from the SDK. It scales extremely well, but it requires coordination between all participants. And there's no way to do dynamic scaling. You need to update all this on all participants. You need to communicate it to the SDK. Yeah, so I'll leave it to Sasha to talk about this.
Thank you, Michael. So yeah, I'm gonna talk a little bit about backup and disaster recovery, and then about how do we protect MPC nodes in trusted execution environments, and then do a wrap up. So about the backup and disaster recovery, so there are really, of course, backups are important. It's easy to do, and it has to be done. And there are essentially three modes here. So operational backups for other backups for key portability, and emergency cryptographic recovery. And of course, for backup, even though it's easy to backup, in some modes where we do generate pre-signatures, you don't backup pre-signatures because it can have an impact on the security. So first, of course, we can export, import individual key shares, do the local backup, and this is something which is mostly used in web browsers and mobile applications, where we can essentially export the key and then the key share, and then re-import it into the new application. Then we can export all the key shares of a given key. Then essentially copy a Builder-Vault instance to a new setup. Or we can also use it for importing a non-MPC key, and then split and have essentially shares between MPC nodes. And finally, there is an emergency recovery service, which is essentially consists in backing up all the nodes shares with a zero-knowledge proof, where then essentially it can be, in case of really last resort and emergency, recombined into the full key, and can be used for whatever purpose. The zero-knowledge proof ensures that actually the ciphertext really decrypts the right private key. So then I'll move to the trusted execution environment and confidential computing. So here, essentially, MPC reduces the risk of a single node compromise, but it doesn't eliminate the fact that at a given moment in time, shares exist in memory, and trusted execution environments close this gap. So one direct question is, if we are using HSMs, why don't we do MPC inside HSMs? And the reason is that actually it involves some high complexity and certain vendor lock-in, because then we have actually to develop some MPC protocols and primitives for a specific HSM. And that's where trusted execution environments and confidential computing provide something complementary. So to encryption at rest, which is provided indeed by HSMs, and encryption in transit, which is provided by MTLS usually. And it's actually very flexible because as of today, many cloud service providers provide some form of confidential computing stacks. So it's something that we implemented first was a confidential computing stack using AWS Nitro, where we, briefly we have our MPC node running inside a Nitro enclave. And what we have done is that we are leveraging the full cryptographic attestation flow of provided by AWS Nitro. So the enclave attests to the KMS its measurements, so the fact that it was not tampered with. It also generates an ephemeral key pair, provides a public key. This is all signed with the Nitro hypervisor, and then KMS, depending on the release key policy, checks those measurements and injects the key material, in this case the MPC share, using the secure channel into the Nitro enclave. So another final thing that we that was challenging, and then we can move to the next slide. We have so we have implemented a custom sort of tooling for Nitro, where we have actually leveraged VSOC for actually running arbitrary networking runtime, which requires networking, because VSOC doesn't provide the native networking capability. So to wrap up our presentation and also the trusted execution environment part, of course there is a lot about sharing best practices that we have shared during this presentation with the customers, and a lot about customer education. There is quite actually deployment overhead where some infrastructure has to be put in place, and this is something we usually forget when we are deploying, or customers are deploying the MPC protocols, which can also have impact on the security. For example, segregation of duties, where in case of confidential computing, you have to separate who is managing the KMS and the verifier, who is able to edit and modify the key release policies. I already talked about the fact that VSOC, even though we have implemented a generic way of doing IP networking with VSOC, it adds to the overall overhead and processing time. We are looking and implementing also the same approach with Azure confidential computing technology, which in this case removes this VSOC overhead. And last but not least, one of the actually questions is how we can, in case of confidential computing deployments, we can reduce the trusted computing base even further. So we are thinking about how to do MPC protocol, like only the MPC protocol processing and computation inside the enclave, and actually take the transport, the storage, and the orchestration outside of the enclave. So now this completes my part, and we would like once again to thank you for your attention. And in case you have any questions, we will be really happy to answer, and you can send them to Jakob's email, and we'll do our best to answer it as quickly as possible. Thank you for your attention.